Right, hello, this is Jishan Chowdhury from JC Tuition, and today we're going to be talking about the ideal gas equation. So Boyle's law tells us that the product of pressure and volume are constant as long as the temperature remains constant. Charles' law tells us that the volume is proportional to the temperature as long as the pressure remains constant. So V over T will be constant as long as pressure remains constant. Gay-Lussac's law, that tells us that pressure is directly proportional to temperature as long as the volume remains constant, so P over T remains constant. And if we just combine these relationships, what we've got pressure times the volume all over temperature, well then these must remain constant for a fixed mass of gas. This is how we derive the ideal gas equation. So let's just break it down. So the ideal gas equation tells us that the pressure, which has to be measured, by the way, in pascals, multiplied by the volume, which has to be measured in meters cubed. The units are very important. Is equal to the number of moles, so we can just know that by N, a gas constant, which we'll call R for now, and it normally has the units joules per Kelvin per mole. Basically, it's telling us this is just a constant for 1 mole of gas. And finally, temperature, which is measured in Kelvin. Okay, so a neat way to remember it is PV equals nRT. Just flows off the tongue a bit more nicely, and is easier to remember. So the other thing to mention is the gas constant is a constant, of course, and its value is 8.31, and we already said the units is joules per Kelvin per mole. And yeah, this is it. So this is the ideal gas equation, and it's called ideal because, well, no gas actually obeys it exactly, but at room temperature and pressure, it holds pretty well for most gases. And when we're working in chemistry, it's useful to imagine a gas which obeys this equation perfectly. The ideal gas equation. So it's PV nRT. And let's just see if we can work out volume. So to work out volume, simply all we do is divide both sides by the pressure. So we divide both sides by pressure, divide both sides by pressure. Well, what we get is volume now is nRT divided by pressure. Yeah. And interestingly, using the ideal gas equation, you can calculate the volume of 1 mole of gas at any temperature and pressure. Now, this might seem a bit odd, but if we just imagine a gas, so these are loads of gas particles doing their random thing. Well, it's not really about the size of the gas particles, it's more about the space between them. And 1 mole of gas will most likely account for the same volume, overall volume of the gas. Even if you can imagine the really large gas particles, it's really small when compared to the space between the actual particles, so they'll still take up the same volume. Let me show you what I mean. So let's imagine, let's just set up a temperature of 20 degrees Celsius and a pressure of, I'm just setting up some conditions, of 100,000 pascals. And let's say we're working out the volume for 1 mole of gas. Well, using the ideal gas equation and rearranged to find volume, we get that volume equals N, so that's just 1 mole, times R, which is 8.31, times the temperature. Remember, temperature has to be in Kelvin, so what we do is we add 273 to convert it to Kelvin, so I'll just write that there, add 273, well, that gives us 293 times, time multiplied by 293, all divided by pressure, which is 100,000. And if you plug that into calculator, we get that volume is 0.0243. Remember that volume is measured in meters cubed, so converting that to centimeters cubed, well, we just times it by 10 to the power of 6, so that is 24,300 centimeters cubed. So that means the volume of any mole of gas at room temperature and pressure is approximately equal to 24,000 centimeters cubed. So 1 mole of sulfur dioxide, which is a mass of 64.1 grams, has the same volume as 1 mole of hydrogen gas, which is much smaller. It's got a mass of about 2 grams. So that's how we work out volume. And you can work out pressure in the same way. So again, if we just go to PV equals nRT, well, to work out pressure, we just divide both sides by volume, so we're just left with pressure equals nRT divided by V. Okay, so let's find the number of moles of any gas. So let's start off with our ideal gas equation again. So we've got PV equals nRT. Well, to find moles, we can divide both sides by this RT here, and that will just leave us with moles. So we've got moles equals PV divided by RT. Okay, so let's say we have the volume of, we'll say this is 100 centimeters cubed, and let's try and work out how many moles of hydrogen molecules are present in this volume. We'll say temperature is 20 degrees again, and the pressure is 100 kilopascals, so standard conditions. So we just simply plug it into this formula. So therefore, number of moles is equal to pressure, which is 100 kilopascals. Remember, it has to be in pascals. So what we do is we times it by 1,000. So 100 kilopascals is 100,000 pascals, and then we times it by the volume, 100 centimeters cubed. Remember, it has to be in meters cubed. So changing centimeters cubed into meters cubed, we just multiply it by 10 to the power of -6. Okay. So that is therefore multiplied by 100 times 10 to the -6 to convert it into meters cubed. And we divide this by R, which is our constant, which you might remember is just 8.31, our gas constant, and multiplied by temperature. Now 20 degrees, add 273, that gives us 293 kelvins. Okay, so it's really important to make sure they're in the wrong units, or you're going to end up with some funky answer that isn't right. How many moles are present in a volume of 100 centimeter cubed? How many moles of hydrogen gas that is? Well, if you plug that into a calculator, we get 0.00411 moles. A bit more abstract, and try and work out the relative molecular mass of a gas. So remember, molecular mass isn't actually in the formula of our ideal gas equation. So ideal gas is PV equals nRT. And molecular mass isn't in that. We do have moles, however, and you might recall we can connect moles and molecular mass. So we know that number of moles is mass over the molecular mass. So if we can work out the amount of moles of gas, then we can use this formula to try and work out molecular mass. So let's go about doing that. So let's look at the question. We've got the apparatus is used to find the molecular mass of lighter fuel. The lighter fuel canister here was weighed, and 100 centimeter cubed of the gas was dispensed into this measuring cylinder until the levels of water inside and outside the measuring cylinder were the same, so that the pressure of the collected gas was the same as the atmospheric pressure. So we're looking for equilibrium here, and they've done that. So the canister was reweighed, and we found that it lost a mass of 2.29 grams. The atmospheric pressure was noted to be 100,000 pascals, and the temperature was 14 degrees. So I already told you we need to work out moles. So to work out moles from this equation, we know that PV divided by RT. So our pressure is 100,000 pascals, and we've got 100 centimeters. So we've got 1,000 centimeters cubed, but of course it has to be in meters cubed. So we need to times it by 10 to the -6. Divided by R, our ideal gas constant, 8.31, and temperature, which is 14 degrees. Remember, we add 273 to that, so that's 287 Kelvin. All right, so let's plug that into our calculator. What do we get? Well, we get 0.042 moles of this gas, and that's in the measuring cylinder. So that means the 0.042 mass. So this has lost, remember, 2.29 grams. So the mass, this 0.042 moles must have that 2.29 grams. Okay, so using this equation now and rearranging it, we get that to get molar mass, the subject of the formula. Well, we times both sides by mR, so molar mass. So that's mRn equals mass. Then we can divide by moles. So we get mR equals mass over moles. All right, so let's use what we know. So the molecular mass of the lighter fuel is the mass, which is 2.29 grams, divided by the amount of moles, which is 0.042. Excuse my handwriting. So the molecular mass is therefore 54.5. So that's the molecular mass of the lighter gas. So that is all I wanted to cover in this video. So I hope the ideal gas equation makes more sense. So remember, it's no gas obeys it exactly. That's why it's called the ideal gas equation. But at room temperature and pressure, it holds really well. So really useful to know, and I hope it makes sense. If you want more resources, please go to www.jctuition.net. All right, thank you.